Okay, for this first video here, we're going to go over two examples of how to go from an approximation of the area under a curve to the exact. We're going to start off with doing kind of an easier one that we can verify geometrically, and then doing another one which we don't have a formula for geometrically. Okay, so to write the problem that I want to be doing right now, I want to approximate the area under the curve f of x equals x over the interval 0 to 1. Okay. Now the reason why this one is okay is that if I do a quick doodle of things, there's 0, there's 1 on my x-axis, there's my y-axis, and this is y equals f of x, which is the same thing as x. Doot, 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 doot. So the area from here to here, well, this length is 1, this length is 1, that's just a triangle, right? So the area of a triangle is the base times the height divided by 2, or it's 1/2. Okay, so we want to remember that 1/2 we know for certain is the right answer. Okay, so let's go through basically 3 steps on how to do this. Okay, step 1 here is that we're going to create a partition. All right, sorry about my weird handwriting here. Okay, and so what this does, what we want to do is we want to take this interval, 0 to 1, and chop it up into n equal pieces. Okay, so if I chop this interval up, like let's just make like a quick doodle of what we're doing here, 0 to 1, and if I chop it up into n pieces, all of which are the same length, okay, we call that length of each piece there, we're going to label that delta sub x, okay, and the ith location here, we're going to call it xi, all right, we always start at x0, and the last one will always be x sub n because I have n pieces, so that's just how the math works out. Ouch. Okay, so first thing we can determine here is the length of delta x, okay, or the value of delta x, and that's going to equal the length of my interval, which in this case is 1 minus 0, divided by how many pieces there are, n, so my delta x here is 1 over n. Cool, all right. Next thing I want to do is, what is the formula for the ith x value? Well, if I look, the ith one, or the first one rather, is I start at x0 and I jump delta x 1 times. The second one is I've jumped it 2 times. Third one is I've jumped it 3 times. So in general, it's where do I start? How many times have I jumped? And what is the length of each of my jumps? All right. And so for us, this is 0 plus I times 1 over n, or just simply I over n. So there, we've done our partition, and I've written down the things that are important for it that we're going to need in a minute here. All right, so step 2 here is we approximate. All right, I'm just going to write the word approx, because approximate is just needlessly long. All right, we're approximating the word approximate. And so we're going to do this with our sort of using rectangles and like the left-hand rule, the right-hand rule, etc. In general, the right endpoint rule here is just going to be like the easiest ones to write down. And what that says is that the area is approximately equal to, we'll sum up from I equals 1 to n, my function evaluated at the ith cutting point, multiplied by how wide my intervals are. And the reason that is, I mean, we can kind of see here, if I draw this, I'm just going to put a few points here, okay? If I am using the right endpoint rule, then my rectangles, right, look like this. Okay. The width of each of these rectangles is delta x, and the height is described by the 1, 2, 3, 4, 5, or 1, 2, dot, 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 I, dot, 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 n cut point. We're not using x0, so we start from 1, we go all the way up to n. What is my function at that partition point there, right? And how wide was my rectangle? See, this is great. Why is this great? Well, I know what f of x is. It is just x, so f of xi is xi times delta x. Now let's plug in the values that I know for each of these things, which is what we did in step 1. So my area approximation is therefore I equals 1 to n, xi is I over n, and delta x is 1 over n. All right, so now I have a summation. I want to be able to solve what this thing is. Well, I'm going to pull anything that doesn't have to do with my index I out. So I have 1 over n squared times the sum from I equals 1 to n of I. Now, you might not know the general formula for this, and that's okay. That's a lot of the topic of 127. And in fact, what we're doing right now is I'm showing you the hard way. We're going to develop easier ways to calculate these things, but this is a nice formal way of figuring out these areas under curves, okay? So this part in the circle there, that happens to equal n times n plus 1 over 2. I say happens to equal. That is what it equals. Okay. So that's going to equal, well, n times n is n squared divided by n squared, and 2 gives me a half. N times 1 is n plus 1 over 2n. All right, so that right there is my approximation. Okay, great. We have one last step to go now. Remember, we're going from the approximation to the exact. All right. The third step here, which is using Riemann, says that the area is exactly equal to the limit as n goes to infinity of any approximation. So to do that, I'm going to put a star there. So it doesn't matter which points you used, any approximation will work. Well, I happen to use the right endpoint approximation and got this, so I can plug that in for this whole expression right here. So it equals the limit as n goes to infinity of 1/2 plus 1 over 2n. This part goes to 0. This part is a constant, so it equals a half. And thankfully, I got a half, which we can kind of see my 2's getting cut off a little bit, and we got a half, which we know is the right answer. So awesome. Like, this is sort of the demonstration of a straightforward, easy example. Okay, let's do a hard one. All right, and we're going to introduce just one last bit as I knock something off my table. Sorry about that loud noise. One last bit of notation here to the whole thing. Okay, so in the previous example there, we were calculating, right, the area under the function f of x equals x from 0 to 1. We can denote that this way using an integral. Okay, cool. We already did that one. So now I want to pose another problem, and I want you to take a few seconds to try to translate this into plain words. Okay. So to just read this, this is the integral from 1 to 3 of x squared plus 1 with respect to x. Okay. As far as the problem goes, what am I trying to calculate here? It's the area under f of x equals x squared plus 1, right, from 1 to 3. And to really show that this is something that we don't know how to do, 4, 5, 6, 7, 8, 9, 10, close enough. Here are my axes. Okay, x squared plus 1 looks like that. And I'm calculating that area here. So if I just kind of make those lines solid, I'm calculating the area inside this object. I don't know any nice geometric form which would give me that area. You probably don't either. So we're going to resort to this method that we've been working with. Okay? So step 1, I want to make a partition. Okay? If you want, pause the video right now and try to do it. Okay? Or you can pause it at each individual step here. So make a partition. Now, for my partition, the distance between each point is going to be the length of the total interval divided by how many pieces I chop it up into. So that's where I get the 2 over n. And then, whoops, not that. Then the value for each of my cuts that I end up doing to partition this interval out is going to be equal to x0 plus I times delta x. That's going to equal 1 plus 2I over n. Is that what you got? Hope so. Okay. Step 2, we're going to approximate, and I'm going to approximate the word approximate. There we go. And we're again going to use the right endpoint rule. There's nothing that keeps you from using any other rule. You can go ahead and experiment with it. This is just kind of usually the easiest one to write down. So the area is approximately equal to I equals 1 to n f of xi delta x, which is the same as the sum I equals 1 to n. Take a look at this. What is f? It's x squared plus 1. Now what is xi? It's 1 plus 2I over n. Holy crap. So I get 1 plus 2I over n squared plus 1 times whatever delta x is, 2 over n. Okay. This is a go, but we can do algebra and work with it, okay? So continuing to work with that, I've got my area here is approximately equal to. Now, blowing this whole thing out, we'll do it in 2 steps here, okay? I equals 1 to n. This whole thing in the parentheses ends up equaling 2 plus 4I over n plus 4I squared over n squared. Make sure that you can tell why this is the same as that. And then I still have my 2 over n. Now I can multiply the 2 over n out for each of these 3 terms and take everything that doesn't have to do my index out. So what I get is, oops, don't get that. 2 over n times 2 is 4 over n. None of that has to do with my index. And so I get that. Plus 2 over n times 4I over n is 8 over n squared. But I still have an I there, so that has to stay inside the summation. 2 over n times 4I squared over n squared gives me 8 over n cubed. The sum I equals 1 to n of, and I still have my I squared. Now, this one you can figure out, no problem. You can come up with a formula for that. These two, you can't. We just did this one on the previous part. This one's a little bit more ugly. And I say you can't. You can. We haven't discussed that sort of thing, so I don't expect you to. 4 over n. Now, 1 plus 2 plus 3 plus 4 plus 5 plus 6. No. 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1 n times gives me n. Plus 8 over n squared. This one is the 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus n. This ends up equaling n times n plus 1 over 2. We may do that in class. And then this I squared business, 8 over n cubed gives me n times n plus 1 times 2n plus 1 all over 6. Now you may be tempted to do a whole lot of simplification to this. And I'm going to tell you to hold on. Don't bother simplifying this too much. Okay? Because let's remember what step 3 is. Okay? Step 3 is to do Riemann. Okay, and all I'm going to do is I'm going to take the limit as n goes to infinity of this big ugly thing. The limit as n goes to infinity of, drum roll please, this one's easy to simplify, so I will, plus 8 over 2 is 4, n times n plus 1 over n squared, that comes from all that term, plus 8/6, whatever that works out to, right? N times n plus 1 times 2n plus 1 all over n cubed. Now, if we remember our limits and L'Hopital's rule and all of that fun stuff, what we know is when we have these like polynomial ratios, the only things that matter are those leading terms, the ones with the highest power. So if you notice here, I'm going to get an n squared and an n squared. So those two are going to cancel out, and I'm going to have that 4. And then here I'm going to have an n and an n squared, and that one's going to limit to 0. So what am I left with here? I've got a 4 from this guy. I've got a 4 from this guy. Okay. Now look at this. I've got an n cubed on bottom. So what is my n cubed term? It's going to be an n times the n times the 2n. So I'm going to have a 2n cubed. So I'm going to have a 16/6. Everything else goes to 0. This term goes to 0, and any combination here where it's not all three of those guys multiplied by one another. Take some time and do it out on your own to really satisfy yourself like, yes, that is indeed the case. Okay. So what does this end up equaling? I've run out of a little bit of room here because I've written large. So I've got 8 plus 8/3, which is the same as 32/3, which I believe is the right answer, unless I'm mistaken. Hope this helps. This is a big rigmarole, but to break down the steps into partition, approximate, and then to use Riemann, I hope that really covers it. Okay? Bye-bye.